Alright, let's go ahead and look at ionic and covalent bonds. We're going to look at the naming, how we write formulas for both of those. But before we do that, let's look at what makes an ionic or a covalent bond. So for an ionic bond, we have something like sodium. Sodium has one valence electron, so one electron in its outermost ring. Chlorine has 7 electrons in its outermost ring. Sodium wants to get rid of its 1 because that 1 extra electron is just too much work to hang on to it and it's not really attributing anything. Chlorine, on the other hand, wants to have 8 valence electrons so that it can have the perfect set out here in its outer ring. So the way these two will help each other out then is sodium can take its 1 electron that it wants to get rid of and give it to chlorine, who wants 1 more. When this occurs, sodium is going to be losing 1 electron, or 1 negative. If it loses a single negative, it's still going to have the same number of protons, and so it's going to wind up with a positive charge, and that makes it a cation. Chlorine, when it gains an extra negative, it now becomes negative. Okay, so they've changed electrons, they've given and taken, and they become positive and negative, a cation and an anion. Well, those positive and negative charges that we've just created, those actually attract each other, just like two magnets. And so what we wind up with is those two then attracting each other and becoming sodium chloride, NaCl. So that's ionic bonding. Ionic bonding is about the giving and taking of electrons. So one loses, one takes the electrons, they become positive, negative, then they attract each other. When you name ionic compounds, the cation stays the same, and so it would be sodium for the cation. And the anion, this was chlorine before. We drop the last 3 letters and add an IDE. So chlorine becomes chloride. And so then this is sodium chloride. Now if we take something like magnesium and chloride, or chlorine, we can see that magnesium has a 2+ charge because it'll actually lose 2 electrons, and chlorine still has a -1. We can't put those directly together because they wouldn't neutralize each other. So what we would need then is 2 chlorine atoms to neutralize that 2+, because now we have 2+ and 2 negatives. So when those join together then, the formula would become Mg, cation always goes first, followed by the chlorines, which would be Cl2. Now when we name this guy with ionic bonds, once again the cation stays the same, it's still magnesium. And then for the chlorines, you would see the 2 Cl2s there. You might be tempted to call it dichloride. Not the case. With ionic bonds, there is no prefixes. This is still magnesium chloride. We know that there's 2 chlorides because we know that magnesium has a 2+ charge, and so when we write the formula, we would know to put Cl2 there. So you do not need prefixes on ionic compounds. Now let's talk covalent bonding. So we've got here hydrogen and an oxygen. So oxygen has 1, 2, 3, 4, 5, 6 valence electrons. It wants 2 more. Hydrogens each have 1 valence electron, and they want to gain 1 more. So in this case, they can't really both give and take because hydrogen wants 1, oxygen wants 2. So if oxygen gives up some, it's not going to meet its goal. If hydrogen gives up some, it's not meeting its goal. So instead, what they have to do is share their electrons. So hydrogen will share one of its electrons with oxygen, and oxygen will share one of its with hydrogen. That way, hydrogen will have 2, and oxygen will gain 1 more, and this hydrogen will do the same thing. So what happens then is they share those electrons, and now as a result, if we go around and look at oxygen, oxygen has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons, just the way it wanted it. This hydrogen right here has 1, 2, perfect. And this hydrogen right here, 1, 2 as well. So now everybody's happy through covalent bonding. And the way we would normally draw this is oxygen with its 2 lone pairs and then solid lines to represent that sharing of electrons. So that is covalent bonds. In the case of naming, if we were to name this, this is obviously water, but if we were to name it according to the proper rules, it is H2O. So we would call it dihydrogen, di for the 2 hydrogens. In the case of covalent bonds, we have to use prefixes because it can vary. And then there's 1 oxygen, so it would be monoxide. Okay, so we changed the second word to IDE. Mono is 1, di is 2. Now a couple other rules: that mono prefix does not go on the first element. So in the case of BF3, there's 1 boron and 3 fluorides. So we would not call this monoboron, we would just call it boron trifluoride. The reader can assume that if there's no prefix on the first word, then there must just be one. So it's in order to cut down on redundancy. So boron trifluoride, not monoboron trifluoride. And then the second one, CO2, we would recognize that one as well. It's not monocarbon, it's just carbon. And then with 2 oxygen, it's dioxide. Okay, and in case you don't have them in your notes anymore, here is all of the prefixes, mono through deca, so that's 1 through 10. These would be the prefixes you use to represent the different amounts of the elements in a covalent bond. Don't use these for ionic bonds, just covalent. And remember that mono only gets used on the second element, never on the first. Alright, now let's look back at ionic and covalent compounds, and how we name them and how we create their formulas as well. So first, let's distinguish between an ionic and a covalent bond. So covalent bonds are when atoms actually share electrons. Alright, let's take a look at a couple of these from the worksheet together. Now the first 2 columns after the compound are element 1 and element 2, metal or nonmetal. This is important because that's what we use to distinguish between an ionic and a covalent bond. So the first one, nitrogen and oxygen. If we look at our periodic table, and I'll sketch a quick outline, and it's okay to be impressed with my periodic table outline. And on the periodic table there is that stair step that represents the metalloids. That stair step is also the divider between the metals, and notice there is a lot of metals, and the non-metals. So the metals, non-metals, knowing that distinction between those two, non-metals on the right, metals on the left, is important. So for nitrogen and oxygen, both of those would be found on this side of the stair step. That would make both of those non-metals. And whenever we have 2 nonmetals forming a bond, it is always covalent. So this element then we would use the prefixes for. Nitrogen, there's 1 of them. Oxygen, there's 2 of them. So it would be nitrogen dioxide. Okay. For the next one then, sodium phosphate. So if we wanted to write out the formula for that guy, it would be sodium is Na, and there would be 3PO4. So phosphate's 3 minus, sodium is plus 1. That is Na3PO4 if you can't read that. So the first element in this case is going to be a metal. And the second ones are both nonmetals. So anytime we have a bond with a metal in it, that makes it a ionic compound. Okay, so if it involves a metal at all, it's always an ionic bond. So 2 nonmetals, covalent. We use prefixes for those. A metal and a nonmetal, or just a metal in there, period, makes it an ionic bond, and we do not use prefixes for those. Alright, hopefully that helps you out a little bit with the covalent and ionic bonds.